we had defined this norm, that is norm suffix p yesterday on these spaces, that is Rn and Cn. Okay. Let us again just recall, that is suppose we take x as x1 x2 xn, then we had defined norm suffix p of this by this formula sigma mod xj to the power p whole thing raised to 1 by p if 1 less than or equal to p less than infinity, and this is maximum over j mod xj if p is equal to infinity. Okay. And in all cases we have proved that this is a norm on Rn, or if you take a similar, if x is in Cn, then it is a norm on Cn. Okay. Alright. Then each of this norm will induce a metric on Rn. Okay. So we can denote that metric also by d suffix p. Okay. So d suffix p of xy, that would be nothing but norm of y minus x suffix p, and that will be by our definition sigma j going from 1 to n mod yj minus xj whole power p, and then this whole thing for 1 by p if 1 less than or equal to p less than infinity, and in a similar way it will be maximum of mod yj minus xj, maximum taken over j for p equal to infinity. Okay. Each of this will be a metric on Rn, and similarly on Cn. The case p equal to 2, okay, let us take the case p equal to 2, okay, then that is called d, let us say d, that is d suffix 2 xy, that is nothing but sigma j going from 1 to n mod yj minus xj square, and then this whole thing, that is square root of the whole thing. Okay. This particular distance is the most popular distance, and that is called Euclidean distance, okay, or Euclidean metric. Okay. As you will realize that if n is equal to 2 or 3, x and y are the points in R2 and R3, and the distance between those 2 points is given by this formula, and that is the usual distance that we that you are familiar with. Okay. That is why this is called usual metric or usual distance. Okay. It should also be clear to you that if n is equal to 1, that if the whole thing is happening in R1, all of these will coincide. Okay. Okay. For various values of p, all this formula will simply come down to just one single formula. Okay. All right. So this is about these spaces Rn and Cn with various metrics. Similarly, for p equal to 2, the corresponding norm is also called Euclidean norm. Okay. That is, this norm suffix 2 is also called Euclidean norm. Okay. Now let us consider a slight extension of these things. Okay. Here we are considering the spaces Rn and Cn. So these are the spaces where the points have n coordinates. Suppose we let the coordinates to be infinity, or which is same as saying that we consider the sequences instead of just n tuples, we consider sequences. Okay. So those are called sequence spaces or spaces of sequences. Okay. And so here the objects are each x is a sequence, so we will denote x as this sequence xi, okay, whose nth element is x suffix n. Okay. The sequence can be of real numbers or complex numbers, okay, depending on the spaces that we are considering will be either real vector spaces or complex vector spaces. Okay. All right. Now one of the spaces we already discussed, okay, that is the space which was L1. Okay, this was one of the first example. What was that space? It was the space of all such sequences x, that is x from n to r, such that sigma mod xn converges, okay, that is xn is absolutely, sigma xn is absolutely convergent, okay, alright. Now in a similar way as we have done here, we can define norm suffix p, okay, we can define norm suffix p. Only thing is that this, now the sum will, instead of going j from 1 to n, j will go from 1 to infinity, okay, j will go from 1 to infinity. So let us now define norm suffix p of x as, in the same way, sigma j going from 1 to infinity mod xj to the power p whole thing to the power 1 by p. This is for 1 less than or equal to p less than infinity, and similarly for p equal to infinity, here we had taken maximum of mod xj, okay, we could take maximum here because there are only n numbers here, okay, so it will have a maximum, but here there are infinitely many, so we cannot talk of maximum, we cannot talk of maximum, so we will take supremum, okay, supremum or least upper bound, okay, so this will be supremum over j mod xj, this is if p is equal to infinity, okay, right. There is one more difference, okay, this norm suffix p as defined here and Rn, that is defined for every x, okay, that is defined for every x, okay, but this norm suffix p as defined here, okay, you can see that that is not defined for every sequence x, okay, it is defined only if this is a convergent series, okay, if sigma mod xj to the power p is a convergent series, then only we can talk of the norm x suffix p like that, okay. Similarly here also you can talk of supremum of mod xj only if xj is a bounded sequence, right. If it is an unbounded sequence, again we cannot say anything about norm suffix infinity, okay, so that is another restriction. So we cannot consider all possible sequences, we have to consider the sequences for which the series sigma mod xj to the power p converges, and in this case bounded sequence, okay. So those spaces are called L superscript p, okay, L superscript p, that is the space, that is all those sequences x from, let us say, n to r, for which this norm suffix p, okay, let us say I will write it this way, sigma mod xj to the power p, j going from 1 to infinity, converges, okay. By the way, let me also say that when the series is of non-negative terms, we have seen that the series converges, it is same as saying that its sequence of partial sums is bounded. So that is why for example what I have written here, many books will also find this notation sigma mod xn strictly less than infinity, okay, that means the same thing, that sigma mod xn converges, okay. So similarly sigma mod xj to the power p strictly less than infinity, okay, that is the meaning of that is that it is a convergent series, okay. Okay, so for such x we can now define norm x suffix p, okay. Of course this is for 1 less than or equal to p less than infinity, and L infinity is the thing but the set of all bounded sequences, bounded sequences, okay. Now we have to verify that each of this is a vector space, okay, each of this is a vector space and this defines a norm on that, okay, then only that will become a metric space, okay, right. Now that is easy, for example in L1 we have already verified, okay, when p is equal to 1 we already verified, okay. Similarly for p equal to infinity, that is easy, suppose if xn and yn these are the two bounded sequences, then xn plus yn is also a bounded sequence, right, okay. And Similarly, alpha times xn is also a bounded sequence. So L infinity is a vector space is trivial. Similarly, L1 is a vector space follows from the properties of the convergent series. Also that this is a norm, as you have seen, as I have mentioned earlier also, that whenever you want to check that something is a norm, only thing that needs real checking is the triangle inequality. Okay. Triangle inequality also for the case p equal to 1 and infinity is again trivial here, okay, right. P equal to 1 we have already seen. P equal to infinity, what will that involve? You will have to take the supremum of mod xj plus yj and show that that is less than or equal to supremum of mod xj plus supremum of mod yj. That is also fairly straightforward thing to see, okay. So let us just look at this particular case, 1 less than p less than infinity, okay, 1 less than p less than infinity. Now to show that this is a norm, what is required to be shown? We will have to show this, that is norm of x plus y, okay, not just that, we will have to show this, okay, that is first thing is this, x and y belongs to LP. This we must show from here that x plus y also belongs to LP. This is what we need to show, okay, and also x belongs to LP implies alpha x belongs to LP, okay. And we also need to show that this is okay. Out of, you can say out of these two things this is trivial, okay. If x belongs to, if sigma mod xj to the power p is a convergent series, if you replace it by mod xj by alpha times xj, okay, mod alpha x is nothing but mod alpha into mod xj, that mod alpha will come outside the summation sign, okay. So this part is trivial, okay, there is nothing to we need to show this, okay, we need to show this, and we should also show that norm of x plus y suffix p, this is less than or equal to norm x suffix p plus norm y suffix p, okay. Alright, what we can do is that if we show this last thing, this will also follow, okay, this will also follow, okay. So let me just write this in the complete expanded form, okay. What is the meaning of this? It means that norm of x plus y suffix p is nothing but mod xj plus yj, j going from this to the power p and then this whole thing to the power 1 by p, okay. This is less than or equal to sigma mod xj to the power p, j going from 1 to infinity whole to the power 1 by p, and plus similarly for sigma mod yj, okay. Whole to the power 1 by p, okay. You remember that we have proved inequality similar to this, okay. Only difference was there, j was going from 1 to n instead of 1 to infinity, okay, right. If we replace j going from 1 to n, we everywhere we already proved this, okay, and that is what we had called Minkowski's inequality, okay. Even this is also called Minkowski's inequality, this is also called Minkowski's inequality, okay. And since, as we have observed earlier, whatever we need to prove about the series, the only way to prove is by going to the partial sums, sequence of partial sums, okay. So suppose we consider the sequence of partial sums, okay, for the time being let us say I will forget about this power 1 by p, okay, I will just consider the partial sum of this series, okay. So what is that? It will be, suppose I call it Sn, Sn is sigma mod xj plus yj to the power p, let us say j going from 1 to n, and similarly let us talk about, give some notation for the partial sums of this. Suppose I call this un as sigma j going from 1 to n mod xj to the power p, and let us say vn as sigma j going from 1 to n mod yj to the power p. Okay. Okay. Let us now look at this. Suppose x and y are in LP. Okay. Suppose x and y are in LP. Okay. Then suppose x and y belong to LP. Okay. Then what does it mean? It means that sigma mod x to the power p and sigma mod yz to the power p, they are convergent series. Okay. They are convergent series. Okay. That means un tends to something and vn tends to some, it has limit. Okay. So this means let us say un tends to, let us say v. Okay. Un tends to v and sorry un tends to, let us say u, and let us say vn tends to v. Okay. All right. Okay. Now do we know any relationship between Sn, Un and Vn? What is that? That is the Minkowski inequality. What we have proved is that this raised to 1 by p is less than or equal to this raised to 1 by p. That was the Minkowski inequality for the finite sums. Let us use that. Okay. So what we can say is that okay, Sn raised to 1 by p is less than or equal to un raised to 1 by p plus vn raised to 1 by p. Okay. Or we can suppose I take pth power everywhere. Okay. Suppose I take pth power everywhere, I can say that Sn is less than or equal to un to the power 1 by p plus vn to the power 1 by p whole thing raised to p. Okay. Okay. Now is the argument clear after this? Does it, what you have on the right hand side, okay, what you have on the right hand side is it a convergent sequence? Yeah. Right, because un etc. Does it mean that it is a bounded sequence? Every convergent sequence is bounded. Okay. Does it mean that Sn is also a bounded sequence? Okay. All right. Okay. Does it mean that Sn converges? Because Sn is monotonically increasing. Okay. Because it's a partial sum of a series of non-negative terms. Okay. So that proves that Sn converges. Okay. But once we say Sn converges, then that is same as saying that x plus y belongs to LP. Okay. Right. So we can I will simply write this implies that Sn is bounded. Sn is bounded. Okay. And we have seen that in case of series of non-negative terms, if the sequence of partial sum is bounded, then the series converges. Okay. Right. And so that means this series converges, which is same as saying that x plus y belongs to LP. Okay. It is same as saying that. So this implies that x plus y belongs to LP. Okay. And we already observed that if x belongs to LP, then alpha x belongs to LP follows trivially. Okay. So that shows that LP is a vector space. Okay. Okay. Now only thing remains to be shown is this last, this one, x plus y etc. Okay. Or which is same as saying that we need to prove this Minkowski's inequality. Okay. Now can you say that once we know that Sn is a convergent sequence, okay, once we know Sn is a convergent sequence, then you go back to this. Okay. Okay. Now this is true for every n. Okay, this is true for every n. Okay. So the limit of this should be less than or equal to limit of whatever you have on the right hand side. Okay. And we know all these limits. Okay. We know all the limits. So suppose limit of Sn is s. Okay. Suppose limit of Sn is s, then it so Sn is bounded. Okay. So suppose Sn converges to s. Okay. Okay. Then what follows from this equation here is that Sn to the s to the power n by s to the power 1 by p is less than or equal to u to the power 1 by p plus v to the power 1 by p, okay. But that is same as this, okay, because this whatever you have here in the bracket, that is s, because Sn converges to this number, okay, that is the sum of the series. Similarly this is u, okay, and that is v, okay. So each of these LP is a norm linear space and hence a metric space, okay. This LP norm will induce a metric, okay. Now just for the sake of understanding, let us see a couple of examples of sequences which belong to some of the spaces or do not belong to some of these spaces, etc. Okay, let us take the sequence 1 by n, okay, or let me write in a full form. Let us say x is this sequence 1 by 2, 1 by 3, etc. Okay. Okay. Let me ask a question. Does x belong to L infinity? No. What is L infinity? It is a bounded. Is it a bounded sequence or not? It is a bounded. It is a bounded decreasing sequence. Okay. Every of non-negative terms. So each term is bigger than or equal to 0 and less than or equal to 1. Okay. So this belongs to L infinity. That is okay. That's no problem. Okay. Okay. Does it belong to L1? Yes? No. Why? Because if you take sigma mod xj, it is sigma 1 by n, okay, sigma 1 by n or sigma 1 by j, okay, that is a divergence, that is not common. So it does not belong to L1. So x does not belong to L1. Okay. What about L2? Because then we will consider sigma 1 by n square, okay, sigma 1 by n square. So it will belong to L2. Okay. So remember now when we are discussing Rn and Cn, the spaces were all same, okay, but when we are talking about LP, for each P the space is different, okay, for each P the space is different, okay, they are all different metric spaces, okay, alright. Can you also see that each of this LP is contained in L infinity, okay, because we know that if sigma mod xj to the power P is a convergent series, its nth term converges, okay, and every convergent sequence is bounded, okay. So each of this LP is contained in L infinity, okay. So L infinity is the biggest possible space among all this, okay. Okay, let me also give this to you as an exercise. Show that L1 is contained in L2. Show that L1 is contained in L2, okay, take this as an exercise, okay. Okay, and those of you who can do this, those of you who can do this, generalize this, okay, take any two numbers P1 and P2, okay, and if P1 is less than or equal to P2, then LP1 is contained in LP2, the same idea will work, okay. Of course do this after your quiz, okay, okay, do this. Okay. Now since L infinity is the biggest possible space among all these, it has also some well known subspaces, okay, right. Let us also talk of some of those subspaces, okay. And those are also have very standard notations. This space which is called small c, okay, okay, this is the set of all convergent sequences. Okay. Is it clear that the set of all convergent sequences is also a vector space, right? If xn and yn are two convergent sequences, xn plus yn alpha times xn, that is also a convergent sequence, okay, alright. Is it clear that that is contained in the infinity? Okay, every convergent sequence is bounded. Okay, all right. Then let me take one more. Okay, call it C naught. It is called C naught. Okay. See, when we take C is a set of all convergent sequences, we do not bother what is the limit of the sequence. Okay. Here what I do is I will take those sequences which converge to 0. Okay. Okay, only those sequences which converge to 0. So let us say, so this sequence X from n to R satisfying the property that limit xn as n tends to infinity is 0. Okay. Is that also a vector space, right? That is clear. If xn tends to 0, alpha times xn will also tend to 0. Okay, and if xn and yn, they are two sequences with the limit 0, xn plus yn will also tend to 0, right? That is a vector space. Okay, all right. What is the relationship between these two? C naught is contained in C, right? C naught is contained in C and C is contained in L infinity. Okay. Okay. Is the inclusion strict every time, right? So we can say, in fact, okay, we can easily find a sequence which is bounded but not convergent. This is small c and okay. Now what about the relationship between all those LPs and this C naught? Yes, that is again an old result. We have seen that if a series sigma xn converges, then the sequence xn should converge to 0, right? So once we say that sigma mod xj to the power p is a convergent series, it means that xj goes to 0 as j goes to infinity, right? Okay, right? So that means each of this LP is contained in C naught, right? Each of this LP, so each of this LP is contained in C naught. Okay, right? Is the inclusion strict again? Can you say that this is yes, and what is an example of, just take this sequence, okay, this belongs to C naught, okay, right, and this does not belong to L1, okay, this does not belong to L1, okay. So here also the inclusion is strict, okay, all right, okay. And then let me take one more space which is also very important. By the way, these notations are fairly standard, followed in many books. Okay. The space which is called C naught naught, I will take this two subscripts 0. Okay. Okay. This is the space of all those sequences where what we say is that all but finite number of terms are 0. Okay. That means in a sequence at the most finite number of xn's are non-zero. Okay. So we can say that so set of all x in x from n to r such that xn is equal to 0 for all n belonging to n minus e, where e is a finite set. Okay, that is where e is a, we can say that x such that let us say there exists a finite set E, there exists a finite set E, that is finite subset E of n such that xn is not 0 for all n belonging to E. No, in fact I should say the other way, actually this is a wrong description. Okay, what I should say is that I say that it is 0 except a finitely many n. So what I should say is that xn is 0 for all n outside E. Okay, xn is 0 for all n, that is xn is 0 for all n not in E, okay, xn is 0 for all n not in E, that is the correct description. That is, there should exist a finite subset of n such that outside that finite set all xn's are 0.
So what is the difference between those two statements?
What
Let's
is
say xn is not 0 when for all n belong to E. I mean this statement.
Okay, think over it, okay, think over it, okay, I will not explain it now because that will take some time, okay. So alright, since this E is a finite set, E is a finite set, I can take some number which is bigger than all of those numbers in E, okay, some number which is bigger than all of those numbers in E, okay. Suppose I call that number n0, okay, that is n0 is a number which is maximum bigger than all numbers in E. Then what can we say about xn for n bigger than or equal to n0? They are all 0, right, okay, they are all 0, right. So that means what we can say about the relationship between C0 naught and C0? C0 naught is contained in C0, okay, C0 naught is contained in C0. Yeah, by the way, so since that means from what I said just now, remember we had seen a property called eventually something happens, okay. This is also described by all those sequences which become 0 eventually, okay, all the sequences which become 0 eventually, okay, that is C0 naught, okay, alright. What is the relationship between C0 naught and LP? Is it clear? Each C0 naught is, sorry, C0 naught is contained in every LP, right, because only finitely many of these terms are going to be non-zero, everything else is 0, right, because if you take a series like this only finite number of terms are non-zero. Of course which finite number of terms may depend on the sequence, okay, for a different sequence it may be a different set, okay, right. So C0 naught is the smallest among all these spaces, okay. As I said, this is sometimes described as a space of all those sequences which are eventually 0, okay, which are eventually 0, okay. And this is sometimes described as the space of all null sequences, okay. In some books use this terminology, okay. If a sequence goes to 0 it is called a null sequence and C0 is called the space of all null sequences, okay. So I think this is enough about the examples of these spaces of sequences. Let us go to the next type, okay. Those are called function spaces or spaces of functions. Here also it is possible to go through various spaces like this, okay.
C double dot properly contained.
Yes, this is also properly contained, right, okay. Okay, can you give me an example which is not in C0 naught but which is, let us say, in L1? Okay, I said L1, okay, I am looking at this C0 naught and L1, 1 by n is not in L1, so give me an example which is in C0 naught but not in L1, which is in C0 naught but not in L1. Yeah, that is right, 1 by n is not in L1 but it is not in C0 naught also.
1 by n.
So what we want is an example which belongs to L1 but not in C0 naught. So what is the sequence? Is it so difficult a question? What about 1 by n square? 1 by n square is in L1, it is not in C0 naught, okay. If the infinitely many terms are non-zero it is not in C0 naught, right, okay. Alright, let us go to the spaces of functions. Suppose let us say E is any non-empty set, E is any non-empty set, okay, and we can consider the set of all bounded functions from E to R, that is, suppose I call, usually this is the notation used, B of E, B of E. This is the set of all functions f from E to R, and f is bounded. F is bounded. Then if f is bounded, we shall define this for f in B. We define this norm f suffix infinity as supremum of mod fx, x belongs to E. Supremum is taken over all those x for which x belongs to E. Okay. Is it clear that this supremum should be finite? Because we are taking all bounded, so there should exist some alpha such that mod fx is less than or equal to alpha for all x in E. So this supremum exists as a finite real number. Okay. So this is a well defined thing. Okay. It is easy to put that this is a norm. Okay. It will satisfy all the properties of the norm. It is obvious to see that this is bigger than or equal to 0. If it is 0, then each of this fx must be 0, etc. Okay. It is also clear that this is a vector space. Okay. Set of all bounded functions on E is a vector space with the usual operations. Okay. F plus g is fx plus gx, etc. Usual what are called pointwise operations on functions. Okay. So this becomes a metric space with respect to the metric induced by this norm. Okay. Okay. Is it also clear to you that this what we have called L infinity here, okay, is the special case of this B of E, right? In fact, every sequence is a function. Okay. So if you take E is equal to n, that what you have called L infinity there becomes this B of E. Okay. Now let me also consider one more case here. Let us assume that you all know what is meant by a continuous function on the on an interval. Let us say take this space which is denoted by C01. Okay. We shall go to a detailed discussion of continuous functions on metric spaces little later, but you all know from your undergraduate courses what is meant by a continuous function on, let us say, the interval 0 to 1. So we take the function f from 0 1 to R, and f is continuous. F is continuous. Okay. Is it obvious that this is a vector space? Okay, it's a vector space. Okay. Do you all know that if a function is continuous on this closed and bounded interval, then it is bounded? Again, a well known property of. Okay. So every function here is bounded. We don't have to say separately that it is bounded. So you can define this this norm suffix infinity here also. Okay, we can define this norm suffix infinity here also. Okay. But here we can define one more norm, okay, and that is as follows. Let us assume that again we shall discuss this in more detail when we study integration, but for the time being let me assume that you all know that every continuous function is Riemann integrable. Okay. That is, if a function is continuous, we can talk about its integral. Okay. So we define a norm of f as follows. Okay. This is also known as norm suffix 1. It is integral a to b mod fx dx. 0 to 1, it should be 0 to 1. Okay. Now is it clear to you that this is also a norm? This is also a norm, okay, and then there is only one problem here which will needs little proof, that is it is bigger than or equal to 0 is clear. Okay. If it is 0, if the norm is 0, it means the integral mod fx dx is 0, but that will not immediately imply that mod fx is 0, because it can happen that the integral is integral is 0 but the function is non-zero, okay, but that is avoided by the continuity, okay. If the function is non-negative and continuous and if the integral is 0, then we can show that the function must be 0 everywhere, okay. That is where this continuity is used, and then all other properties are easy, okay. For example, to show that norm of f plus g is less than norm f plus norm e will follow from the similar properties of the integrals, okay. So this is also a norm linear space with respect to this norm, okay, and that will also induce a metric, okay. And just as we have done here, one can similarly define the spaces with various values for p. For example, I can take this to the power p and then this whole integral to the power 1 by p, etc., and one can define the various metrics on this also, but again to show the triangular inequality it will require proving some inequalities involving integrals, okay. Those are also well known inequalities, okay. Those are also known as Holder's inequalities, Minkowski's inequalities, etc., but we shall not go into those things right now, okay. So I think now you have got sufficiently many examples of metric spaces and a large number of them are norm linear spaces, so that any concept that we discuss about metric spaces here you can look at all these various examples and try to understand what exactly is happening, okay. Alright, now let us go to some general theory of metric spaces, okay. So for the general theory let us take an arbitrary metric space xd. Let us say xd is a metric space, okay. Then once something is a metric space, what we know is that this d is a function on x cross x, that means given 2 points in x and y, x y in x, I can talk about the distance between x and y, okay. I can talk about distance between x and y, okay. Now let me take slightly different issue here. Suppose I take, let us say, x at some point in x and a is some subset of x, okay. Let us, to avoid the triviality, let us take non-empty subset, okay. And suppose I want to talk about the distance between x and a, okay. I want to talk about distance between x and a, okay. Okay. What is the most natural way of defining, because a will have so many points, okay, a will have many different points, so what should be taken as definition of distance between x and a? Infimum of L, okay. Of course one can take minimum, but minimum may not exist, okay, minimum may not exist, and so what we do is we take this infimum of all these points, like distance between x and a, for taken over all small a belonging to p, okay. Okay, alright. And why does the infimum exist? Yeah, certainly it is a non-empty set, okay, because we have taken as non-empty, yeah, and it is, distance is always bigger than or equal to 0, so it is bounded below, okay, and every non-empty set bounded below should have an infimum, okay, follows from the LUB axiom, right, okay, okay. So this is a well defined thing, okay. What if x belongs to a? The distance will be 0, right, okay. What about the converse?
X does not belong to implies distance is not equal to 0.
Okay. Okay, let us take R with the usual metric, okay. Let us take R with the usual metric, okay. So suppose I take x at 0, okay, alright, and a as 1, 1 by 2, 1 by 3, etc., 1 by n, okay. So what is distance between x and a? Okay, it is the infimum of mod 0 minus 1 mod, okay, it is, so it is infimum of 1, 1 by 2, etc., and what is that infimum? That is 0, okay. Now does x belong to a? No, right. So it is possible that the distance between x and a is 0, okay, but x may not belong to a, okay. So the converse is false. If x belongs to a, distance is 0, okay, but the converse is false, okay. It is possible that x does not belong to A, but the distance is still 0, right, okay. Okay. Now here I have taken a point and a set, okay. Now let us go to the next thing. I can also take two sets, okay. Suppose I take say two sets A and B, let us say both are non-empty. Anyway, A I have already taken, let me take one more set, non-empty set B contained in X, okay, alright. And suppose now I want to talk about distance between A and B, okay. Again the most natural way of defining that is you take all possible pairs of points, one in A and one in B, and take infimum of all those numbers, okay. So it is let us say infimum of distance between say X and Y, where X belongs to A and Y belongs to B, okay. Alright. Can you see that this is nothing but a special case of this, okay. You can take here B as a singleton set X, okay, singleton set X, okay. So that is the same thing, right, okay. Now one more thing, so suppose A and B have a non-empty intersection, okay, that means suppose there is some point common to both A and B, then what can we say about distance? Distance will be 0, okay, distance will be 0. Can you say the converse also holds? Suppose distance is 0, then can we say that they must have at least one common point? Again no, you can again take a similar example there, okay, okay. The two sets can be disjoint, but still the distance may be 0, okay. In fact one can also construct better examples there, okay. For example, suppose I take A as 1, 1 by 3, 1 by 5, etc., and suppose I take B as 1 by 2, 1 by 4, 1 by 6, etc., okay. Then these two are disjoint sets, right, okay. But what about distance between the two sets A and B? Distance is 0, okay. Then we also need one more concept, what is called diameter of A. Okay. Again, if you look at the diameter, idea of the diameter of a disk, okay, then it is nothing but a biggest possible distance between the 2 points, okay. We basically use the same idea. So take any 2 points, look at their distance, and then take the supremum of all those, So diameter of A, we will denote this by this diameter of A, that is supremum of distance between X and Y, and where X and Y both are in A, where X and Y both are in A, okay. They take all possible pairs and take the corresponding distances, and then that will be take the supremum, that will be the diameter. Only thing is that we do not know whether this set is bounded above, okay, we do not know whether this set is bounded above, okay. Only if this set is bounded above, then we can talk about the supremum, okay. So it is in cases like this that extended real line comes into help, okay. So what we can say is that if the set is unbounded, you take the supremum as infinity, okay, you take the supremum as infinity. So in that case we will say that the diameter is infinity, okay. If this set is unbounded, we take that the diameter is infinity, okay. And now important definition, we will say that the set A is bounded if diameter is finite, okay. So A is said to be bounded if diameter of A is a finite real number, okay. I will simply say diameter of A is strictly less than infinity. Remember, it will be always bigger than or equal to 0, okay, it will be always bigger than or equal to 0, okay. If it is a finite real number, then the set is called bounded, okay. we had defined what is meant by a bounded set in real line. Okay, we have defined what is meant by saying that set is bounded below, what is meant by saying that set is bounded above, and we have said that if the set is bounded above as well as below, that will be called a bounded set. Okay, now we have extended that concept for any subset of any metric space. Given any metric space, you can say what is meant by a bounded set. Okay, what is meant by a bounded set. Okay, now I shall give it to you as an exercise. When check that in the case of real line, this definition of bounded set coincides with the earlier definition of bounded set, because now we have two definitions, right. Okay, because suppose you consider real line with the usual metric, by this definition bounded set will be in the set whose diameter is finite, okay, whereas we have already defined bounded by some other method. Okay, now check that these two definitions coincide. Okay, right, these two. There should also be one more very important thing that you should realize. Okay, well, I will just make that and then we will stop. This diameter depends on what is the metric. Okay, it is the distance between, so it can happen that the same set is bounded with respect to one metric and not bounded with respect to some other metric. Okay, is that clear? Is it also clear to you that suppose we have defined what is meant by a discrete metric space. Okay, right. So suppose A is a subset of a discrete metric space. What can we say about this? Because this number has to be either 0 or 1. Okay, so the diameter is always less than or equal to 1. So every set in a discrete metric space is bounded, every non-empty set in a discrete metric space is bounded. Okay, fine, we will stop with that.